Okay, so let us get going. Good evening, everyone. Today we have a very interesting colloquium, I must say. Just seeing the title itself, it makes quite exciting to know someone is going to talk about an instrument, somebody is going to talk about the physics that comes out of this instrument. That is what ASSET is about, right? I mean, you say what you built in the lab and then what kind of physics that gets published due to that. So very much like all of you here, looking forward to hear from Sourav on instrumentation for high resolution laser spectroscopy and laser cooling experiments in TIFR. It's customary to say a few words about today's speaker. Sourav did his BSc from Presidency College way back in 2005, followed up with a master's in SN Bose National Center for Basic Sciences to obtain MSc, and then thereafter he shifted to Purdue in 2007. In Purdue, we built an apparatus for studies on ultra-cold polar molecules and demonstrated the production of ultra-cold molecules using photoassociation. So that's the kind of work probably he continued later. He returned back to India in 2013 at RRI. And so he developed new ion cooling methods based on atom and ion collisions at the Raman Research Institute, as I said, in 2018. And thereafter, he is with us at TIFR, and where he leads a lab now that performed experiments about which he is going to speak today. Over to sir.
Okay. Yeah. Thank you very much for that introduction. So, am I audible? Okay, good. Okay, so since the outline is already there, it's good. So I'm not going to elaborate on that. So my idea is to tell you a very basic introduction on why laser spectroscopy is important, what are the different kinds of laser spectroscopy, and what are the interesting physics you can probe. So it might sound like a very old, very beaten path, but it still produces new results, and I'll introduce you why it is important. And then I'll go on to our results from our lab on hyperfine splitting measurements on 7D state in cesium. And we use diode lasers for these measurements, and some of these we make in our own lab. So I will say how we make them and how we achieve this kind of very precise measurement of hyperfine splitting, which is around 20 times better than any other already reported ones. And towards the end, I will say how we use the same lasers to do laser cooling, and the apparatus is basically completely, almost entirely built in TIFR, or at least with some help from some industries in Pune. So let me just, this is going to be the last slide, but I thought I should. So this is the apparatus actually for the laser cooling one. And so this is where we trap and cool atoms, and most of it is built either in TIFR or in this company called Sourav in Pune, some parts there. And I should start by sort of acknowledging the people who have done the majority of the work. Has been working with me, a student for 4 years, and he is responsible for majority of the work on this hyperfine splitting, and he is also involved in making this laser cooling apparatus. We have many project students who have worked in the lab and contributed in bits and pieces, and currently we have 3 students who are sort of learning and trying to take things forward. We have been majorly supported by the central workshop, so thank you everyone for the support. And I listed here the names of people whom I actually interacted on a daily basis at some point of time, like every day. And I'm saying, like Satpute would say, "Aapka har kaam itna critical kyun hota hai?" So yeah, so I really appreciate this from the work from the workshop. I'll show you some of the details of what they make, a few of them in the talk. And initially, setting up a lab is a very big deal. And the purchase section has been very, very helpful. I mean, the right from explaining how to get things done and not get stuck. So I would like to thank even the purchase section, although I understand this is not customary, but it is really a very big, important thing. Okay, so now to start with the physics part is, I start with very simple thing, hydrogen atom. So we know sort of, we learn in very basic quantum mechanics that this is the spectra energy levels of hydrogen. These ends are the principal quantum numbers, and you have the orbital angular momentum. So for each n, there can be n minus 1 orbital state. So L equal to 0, 1, 2, they are called as PDN. So this is what you get by solving the Schrodinger equation, which is a non-relativistic equation. And what you note is that the energy of the S and P states are degenerate, so they have the same energy. And so people initially when they found they could find the transitions and the transition energies, and initially all the Schrodinger equation were able to match with the experiments. Then came better experiments, so more higher resolution experiments. And what it indicated is that these 2p states actually are not a single state, not a single state, but there are two states. And this could be explained by this Dirac equation, which is a relativistic version of this hydrogen atom. So here, if you take into relativistic corrections into account using the Dirac equation, what happens is you take into account the electron spin, and therefore all these p states, for example, you have to, which are angular momentum equal to 1, you have to add the electron spin, which is half. And so you have now, which is 1 plus half or 1 minus half. So there are two states which are possible. So these are P1 by 2 and P3 by 2. These are called J's. These are the ones in the subscript. And these for hydrogen, the P1 half and P3 half things, these levels are split by around 11 gigahertz. No, these are much smaller compared to what this energy scale is. This is like 10 to the power 6 gigahertz. So it's a very small splitting. So they are split. But these two states, S and S1 by 2 and P half, they are still degenerate. And so this could be explained. So this is what was initially, and then the Dirac's equation could explain it. But then in 1947, there is a very precise measurement from Willis Lamb, who found that actually there is a shift between these two levels. So Dirac says that these two levels should have the same energy, but actually there's a difference, and this is called the famous Lamb shift. It's around 1062 megahertz or around 1 gigahertz, and this led to basically a Nobel Prize for Lamb, and also many started the field of quantum electrodynamics, for which there were many other Nobel Prizes. So a very simple spectroscopy, higher and higher resolution, giving you new physics, and so basically you are making new discoveries. Not only that, if you zoom in further, what you see is that each of these levels are split further. And this now is an interaction between the electron, which is rotating, which has some angular momentum J, which is a combination of the orbital and the spin part. And that interacts with the nucleus, which has a magnetic dipole moment. And this magnetic dipole moment of the nucleus depends on its its nuclear spin. So if the nuclear spin is I, then it will have some kind of a nuclear magnetic moment. I label this as mu L, and this rotating electron, this angular momentum, creates some kind of a charge which is rotating. So you can think of it creating a magnetic field at the location of the nucleus. Therefore, you have this mu kind of interaction, which is a dipole placed in a magnetic field. And see, mu depends on the I, which is the nuclear spin, and V, the magnetic field that the electron creates, that depends on the J. So you get a term which is I dot J. And you can write this I dot J, you can sum I plus J and write as a new quantum number, which is F. And therefore, you have to define this new quantum number, and this energy is basically because of this energy interaction, these levels will split. So this is called hyperfine splitting, and it is it's hyperfine because it is much smaller than fine structure splitting. Fine structure splitting is this fellow, this P1 by 2 and P3 by 2. That's called a fine structure splitting, which is there. So it's a much smaller splitting. So now and now what is important to note is that the how strong this interaction is depends on the probability also of the electron to be present near the nucleus. What I mean is the wave function of the electron, there should be some part of it in near the nucleus, which means S states of electrons will have higher hyperfine splitting compared to P or D states, which are not likely to find them, less likely to find them near the nucleus. So you will see that this whole, I mean, the other states have lower hyperfine states. The ground state, this is the ground state. Now, this part is not to scale, but ground state of hydrogen has this two S equal to 0 and 1. So basically, hydrogen has the nucleus spin 1 by 2, and this J is 1 by 2. So 1 by 2 plus 1 by 2 is either 1 or 0. So we have two S states. They are split by 1.42 gigahertz. And this, in terms of wavelength, is 21 centimeter. That is what basically you have a hydrogen measure with that. astronomy, people use this to detect everything outside the Earth, basically. So this is a very nice tool, and you can make clocks out of it. So it's interesting. People are basically pushing to more and more precise measurements of all these things. Okay. So now, in our lab, we don't work on hydrogen. What we do is we don't have predictor, and we work on the other ones on this group 1 element, which all of which share the common property that each of them have a single electron, single valence electron. So the electronic structure of all these, what we call lithium, potassium, rubidium, and one electron, so their electronic structure is same. So we work with these kind. Hydrogen is more difficult for us, and also the other reason is that this energy takes, so we do laser spectroscopy. This 10.2 is very difficult to get. So typically we work with these alkalis. I'll focus on two. One is this cesium, and later onwards on lithium. So let's look at the cesium structure at the electronic energy levels. Similar to hydrogen, the ground state is a S. Now instead of n equal to 1, now n is equal to the principal quantum number is 6. And so that's the ground state. These are nuclear spin 7/2. So therefore there are 2 F states, which are split by 9 gigahertz. And this is what the state which is used to make to define the unit of time, which is seconds, right? So this transition is measured in some laboratories across the world, and that is what defines what is the time standard of today. So these are called cesium clocks. And these are the excited states. So the first one is P1/2, next one is P3/2. We sort of are interested in measuring these splittings basically in our experiments initially. What are the hyperfine splittings? And this also is used in laser cooling. So that's why I'm not going to talk much about this P1/2 state. So these other states going from the S1/2 to the P3/2 state, they have a nice property that if you excite an atom which is in F equal to 4 to F equal to 5, then this atom in this state can only decay to F equal to 4 and not to F equal to 3, because the selection rule, which has not come up here, which says that delta can be only 0 plus minus 1. So it cannot change by more than 1, either 0 plus minus 1. Similarly, n can be 0 plus minus 1. So this means if you can somehow, so if we can pump all the atoms to F equal to 4 and then keep it on, which is tuned to this 4 to 5 transition, the atom will and come down. And it keeps doing it. So these are cycling transitions. And every time it absorbs the photon, it gets a momentum kick from the laser, because the laser has some finite momentum. H by k is the unit. The photons have finite, and this is what is used in laser cooling. Okay. Actually, the structure for lithium is similar. You can see exactly the number basically change, and sometimes there is a minus sign on, but the structure is the same. So all of these alkalis you can do laser cooling on. Hydrogen you could do laser cooling, but this wavelength that you require is 121 nanometer, which is not sort of possible. And all these lasers are basically continuous wave lasers. Okay. So now let's see how do we measure this excited hyperfine splitting. So you could take a cell of cesium vapors, which is just a glass cell, pass a probe light through it, and tune the frequency of this laser, and measure its spectrum on a photodiode. You look at the transmission, you will get a picture like that. You don't see any of these narrow lines that you would expect for excitation to each of these states, which are very narrow lines of the order of 6, 7 megahertz or 5 megahertz, something like that. The width in this spectrum is about half a gigahertz. And this is because of the lines are Doppler version. So you have atoms moving around. So the laser goes, but different atoms moving at different speed, absorb at a slightly different frequency. So if the transition frequency is F0 and the velocity of the atom is V, then depending on whether it's moving towards the laser or from the laser, it will absorb at a slightly different frequency, and therefore you have a broad spectrum. So to get rid of this thing and you get a better spectrum, one thing you can do is that instead of using just a vapor cell, you make an oven and make a collimated beam of atoms. So put slits, and make a very nice collimated beam of atom, which is going in one direction. In the other direction, it doesn't spread much. And then you interpolate with a laser which is perpendicular to it. Therefore, the velocity in the direction of the atom beam and the projection on the laser beam is 0. So you get rid of this Doppler version. This is the best sort of spectrum available for the cesium S to P transition, where they have just the same around the same region, but now you see this Doppler signal vanish, and you have these sharp lines going from the ground is equal to 3 to excited is equal to 2 or 3 or 4 transitions. And this hypersign splitting was measured. And once you measure it very precisely, you can not only comment initially I said that the nucleus has a dipole, magnetic dipole moment, but it could be slightly deformed. It could have a quadruple moment. It could also have a triple moment. So if you measure it precisely and if you model it correctly, then you can not only measure the electronic property, but remember this hypersign splitting depends on the electronic wave function and also the nuclear properties. So if you can determine if you know the electron property, you can determine the nuclear property, and if you can sort of try to help play with them and get them to be accurate. Yes, Sujit.
So about what is the 500 megahertz bit?
Yes.
And what would be the one in the below?
This one?
One of those.
One of these is around 6 or 7 megahertz.
500 to 6. Oh, two are the magnitude.
Yeah. So these are basically almost close to the natural line width of this transit, which is around 6 megahertz, slightly more than natural line width because there are transit time warnings and so on. So we're almost at the natural line. You cannot get narrower. Almost cannot get narrower.
And the curves are actually logic or just bits?
These are fit to. Sorry, it's fit. So I'll tell you. It is not exactly. It's just a small. It's a wide profile. But so it is a combination of Lorentzian and Gaussian, but the Gaussian is very small, so it is almost a Lorentzian.
That information you get from the white equation. How much is Gaussian, how much is Lorentzian?
White has both components, so we will try to see both and see which one. But in our case, both are sort of similar. So there is Gaussian, but in this one, it is mostly Lorentzian. Yeah. Okay, so this is one of the experiments which actually measured for the first time on optical moment in cesium, magnetic optical moment in cesium. Okay, so this one requires a very sophisticated sort of high vacuum chamber. So in the lab, we typically what we do just in the vapor cell, which is you can buy a vapor cell with a couple of $100, and what you do is a pump probe experiment. So imagine that you are tuned to one of those transitions. You pump a strong pump. What it does is it takes now the atoms from the ground state and puts in the excited state, and you put a probe beam from the opposite direction. Now, if the atoms were at rest, they would then it's the pump of the probe, they interact with both because it's not moving, so there is no Doppler shift. So at the visual velocity, the class of atom interacts with the pump and the probe. But what the probe sees the fraction of atoms which is in the ground state within the pump is much larger. But if you put the pump from this state to excited state, and the transmission of the probe increases, which is what you see when you go to the resonance, the transmission suddenly increase. So you can use this to get this on top of the Doppler modeling feature. You can get this line widths, and because you can typically you put another probe beam which doesn't interact with the pump, and you subtract these two signals. And then you can get these nice Doppler-free sort of almost Doppler-free features, and just similar to the earlier slide spectrum. There is some background which we can do better. I will show you better plots later, and you basically measure these splittings in this. So this is for remember this is for S to P transition. So we are using a one photon transition going from S to P. So what we are going to, so this is a typical setup for this kind of saturated absorption in our lab. This is a 2 feet by 1 feet setup. This is a laser which I'm going to talk about later. These are typically made in TIFR, and this is what we use for this kind of spectroscopy. There's another spectroscopy, which is what we use for this hyperfine measurement of cesium V state, which is a 2 photon spectroscopy. So now, so just go to, if you go to hydrogen, if you want to measure from 1s to 2s state, that's not dipole transition. So what you allow is you can go to 1s to 2s, and if an atom is here and absorbs 2 photons from 2 beams which are coming in opposite directions, then this signal is Doppler free. Because if they are supposed to be moving to the right, from this beam, electrons share it is a frequency f, which is exit 1 minus v by c. But for this beam, it will see a frequency which is moving towards the beam as 1 plus v by c. If you add them up, you see you get 2f0, which is exactly the transition frequency. And this will be true for any velocity class of atoms. So you earlier in a certain class, only zero velocity class was giving a signal, but now all the atoms which are in the interaction zone is giving a signal, and it is WFC. So it's a very strong signal, relatively speaking. But just to the only comment that this transition is still very weak. The two photon the strengths are weaker. So this is what is used to solve here. I cannot tell you the number of protection. So if you want to see a one photon transition typically in this kind of experiments, 1 millimeter will saturate 1 millimeter of laser will saturate your transition. Here, even with 1,000 milliwatts, so 10 to the power 3,000, we will not even see anywhere close to saturation. You still in the linear regime. So to saturate, we will 10 to the 6 or 7. So the
photon is 10 to minus 12 centimeters.
So that 6 orders of
million times.
Million times at least. Yes. This is a much weaker transition. Yes, that's.
Can I reveal my complete ignorance?
Yes, please.
Aren't two photon generically 100 one photon? Just E square over H plus. No.
Wait.
So,
Fine, two factors of E. Okay, with no energy. Okay, anyway.
No.
Two factors of the coupling mass. Okay, never.
No. Okay.
no.
Okay, I did not use that. Okay,
Sorry.
that's fine. That is
omega going into both sides. The coupling is the electromagnetic coupling is parametric. That's what. Even between the photons, photon and that.
So for the way to think of this is you can think of it, if you want to think of in one photon picture, that this photon is also driving a one photon S to P transition. You can think of it, which is very far detuned. So this P state is, and this is used actually in some extent, where if there is some coupling between S and P, then this thing is driving the thing a very far detuned line, which is driving some S to P transition. If there is some coupling between this, always there is in a real atom. Yeah. Okay. So again,
Photon emissions, yes.
whether you go from here to back,
Photon emissions, meaning from the down upper
upward to downward,
there are some
yeah, so this is very weak.
very
And it's what happens is typically the possible decay of C state. So it's calculated to be very weak. But even experimental to make it very difficult because even much stronger decay from H will go to P and then P will come back. So that is what is. So I don't know. It's certainly not less than 10 to the power 7, 8 kind of thing in terms of
absorption is because you have lots of active layer going on. But
See,
emission means
so the emission are extra channels. So emission is that what can happen is that see absorption is that you're going from wireless to 2S, you are so you can do the 2P is here. So the 2P is 1 by 2 is here, or 2P direction I forgot. Let's say 2P is here. So you will have some decay channel from here to here. This has to be one single photon allowed. So that's when it is coming here with 2 photons are not becomes very difficult to us. It will come with 1 photon. So now you have to distinguish between. Yeah, you are stronger. And here if you have the example detect this strong background from the scatter of the light itself. So you want to detect it differentially at a distant wavelength. So I don't know exact numbers for this. It's much bigger. So these are the number also. I forgot. Okay, so this is 2001. This 1s to 2s transition in iron. It's 10 to the power minus 15 precision in this thing. And interested in doing hydrogen because last year I think paper that basically track and cool anti-hydrogen, and they want to do spectroscopy and anti-hydrogen. They have done it as not at this level of precision. So theoretically, they should have exactly the same energy levels separation. So if they want to see the difference between those two things, then it integrates basically physics beyond standard model. So there is some interest in this. What we do in cesium, so the reason we choose cesium going from the lightest one to one of the heaviest one is because a lot of high atomic number. So other contributions, one of which can play a role, which is which people, one of the things is disparity non-conservation interaction, which goes increases with Z. So this is an experiment which was done around 20 years ago now. So looking at this 6s to 7s transition by one photon, so a single photon, which is not allowed. It can only be allowed if this 7s is has some character of P state, which is invoked in this, and this can be caused by this kind of PNC interactions, which can mix some amount of P character because the 6p state, 7p state, which mixes some P character in the S state, and if that happens, then this transition will become weakly allowed. So this is what they measured, and from this measurements, they sort of measure what is known as nuclear anapole moment. But this is, I think there are questions with some of the results from similar studies, but we do not match with experience. So people are interested in still pursuing and seeing if
The impure character comes because of the anapole.
Yeah, so there is some PLC anapole moment. Anapole moment also anapole moment, I think it's parity non-conservation gives you this Z-boson or something. I don't understand the theory of this thing, but yeah. Okay, so what we are looking at is S to D transition. So there is similar kind of concept. Now, this S to D transition recently, this is a paper in 2014 where people have said that actually, if you do this transition precisely, you should be able to make comments on the atomic PMC parity non-conservation. And okay, why suddenly go from S to D? What was great about S is that it was a spherical symmetric thing. The calculations for them are extremely precise. Somehow cesium, so hydrogen is well known, cesium is very well known. Anything in between is not as well known. And that's because experiment that people after experiment on cesium, then some input go into theory, they modify it, try to explain things. So, so it's impressive that the ground state hyperhand splitting of cesium can be predicted to 0.2% accuracy calculated. So it matches at that level, which is a very so many electrons, so not easy things to do. So now the state of the calculation said if you make the state, that also has compact level of at precision in calculation. So if you do experiment, you should be able to make comments. So it's one of our modifications. So now what we do is from S to B state, this is a 7D state, and try to measure one thing we measure is hyperfine splitting in this state. And excitation, what we look at is this fluctuation that comes out when the atom decays from D to P state, one of the P states. And we choose a decay channel which has the highest branching ratio. So signal is strong. So this it's not like this is the first time we are doing it. We have done this 3 or 4 experiments are there, but we are detecting some other channel. So we have some advantage in. So for example, if you detect this, you could detect the P to S channel. So after coming in, you could decay there. But the problem is detecting in ground state, this photon. So your signal will go down. So you need to detect this kind of thing. And the other thing is we want to make the splitting, so we want a very minimal scan of a frequency, which is what we do using a device called an acoustic modulator. Conceptually, we send one beam, the 2 photons focusing and reflecting in that. That is going to be exciting some atoms in the cell and we are collecting fluorescence and detecting on PMT, photomultiplier tube. And now we scan the frequency of the laser, but using the acoustic modulator. But what we do, so basically it's a device which is a crystal, typically it's TO2 crystal, and we apply some RF on it. And this basically is a sound wave, so it causes stress in this crystal, and therefore you have a diffractive index sort of periodically varying diffractive index spatially. And if a laser comes in, it sees this change periodic refractive index variation as a sort of a diffraction phase diffraction rating, and therefore it diffracts. And once you diffract, this frequency of the laser shifts exactly equal to the RF frequency that you have supplied. It could be L plus FRF or FL minus FRF. The plus one would be in the other direction. So we block this zero, which is this first order is what we use. Now, if you change the RF frequency, this frequency will change because we change in the RF frequency, which you can do very minimally using this kind of RF signal generators. So now the problem is, not only does if you change the frequency, the direction of the beam also shifts. It changes. So if you it will keep changing. If you increase this RF, it will keep different. You have to take care. So it will not hit the atoms basically where we want it. So this is solved earlier also. So what you do, you put two lenses here, and you put the focal point. This reflection is the focal length because of parallel ray, and then reflect it back. When you reflect it back, it reflects this part, and then only because of this short the diffracted beam goes in the other direction. So it's going to completely replaces this part. And its frequency is now SL minus 2RF. Now, if you can do it precisely, when you have a beam whose frequency you can tune very precisely, and its direction will not change. So that is what we use in our experiment. So what you do, next slide, sorry. So what you do is suppose you sending it in, so the same reflecting previous basically, you put quarter wave plate. So the ones and then reflects back, right? So the first flow of reflection is basically half wave plate. So the one getting transmitted will not be reflected of the pot. So that we separate the initial beam for the two beam. So in this is the setup basically the schematic. So we split into two parts. One part we send it to this A1 whose frequency, let's say we keep it 100 megahertz, which is fixed. And then we shift it by this 2 into 100 and send it back this line to this cell, cesium cell, which is cesium cell 1, which is actually shielded with sort of less than 10 milliwatt. The person who made this, and this can be bigger, so we know very precisely what is the how well we cancel the magnetic field, which is important. And then this tunes how to exact cluster one of these transitions from 3 to 4 to photon transition. And therefore, we can collect the positions, and then the positions will drop. So we can use this as feedback to the laser and keep the laser on this F equal to 4 transition. Now, what we do, the other part of the beam, we send to another AOM, which is also sent at 100 megahertz, and then we send and send to the cesium cell 2. But now we change the frequency of this AOM. If you change the frequency of the AOM, then this part of the beam is changing. But remember, there is a reference to here. So any change basically on initial thing which I know. So I can do a very precise scan this and measure the splitting. The one complication is that when you do this scan, it's not essentially power changes. So we have to basically look for stabilization. So a few loops, intensity, some stabilization loops we have to make. So again, we do it and we compress. So we can power states the beam reflect, and we basically use this for spectroscopy.
Was the input power of the laser?
No, it does not need to. We need only the light which is going to the cesium cell to be. I'll tell you. So after it goes through the ion, it is now we just enter the cell, we pick off part of the light with a beam splitter and feed it to intensity stabilization circuit which we made. This controls a voltage control attenuator which goes to amplifier which controls the AOM. So in this case, if we have a reference input, I put a reference input and always keep that power going into the cell at that level. Yeah, so we stabilize it to around 0.2% the power of the input. So because these are two different processes, we want to be careful that one small changes in power can lead to a signal asymmetry in the shape. So this is a signal from when we start from a ground state to the D3/2 state. 2 plus because we can excite atoms from the ground F equal to 3 state, also from the ground F equal to 4 state. And this is the excited states. Okay. So see, we need because this cell is basically making sure that the laser frequency is not drifting.
It's a locking.
It's a lock. So If you don't do this, then you put for many it's a fixed, but for even small liters are important. So one this cell is used to do spectroscopy and it gives a feedback to the laser and locks it. So it says that this it is locked onto this transition. So it's laser. So this transition is CVM transition. That is not going to change. So if I can put electronic feedback and lock the laser, then the frequency is not fixed. So the rest of the part is this other one, which now takes that frequency which is fixed now and changes the frequency around the center point. And this we can do very precisely.
Is getting the thermal. What follows the inherent like this?
Thermal, mechanical,
What controls it? What is the control signal? What it does it do to the?
okay, so I'm showing a signal. So the when I explain how the laser works, so basically the laser has a piezo, it has a current, so you want feedback, so you can tune the laser's length with a piezo, so it gives a feedback to the piezo and connects for any drips. And I'll tell you a little bit of how we do it in the
So
Excel.
it might help if you just say what the line width of the laser is.
The line with these hyperfrequency we build that in our lab for megahertz.
Yeah,
So
so
500 kilo.
it is very easy for them.
Yeah, it's a very sensitive thing. And the line is here around 2 megahertz. So I'm trying to measure something which is really narrow. So this width is about 2. So I want the
Length of the
length, mostly on the length of the kite. Yes. So that's what. Okay, so these are the two. So this hierarchical splitting is for the excited state. So whether I excite from the ground F equal to 4, F equal to 4, they are the same. So I have a consistency check. I can measure the splitting here and here and here and compare it with them. They should be the same. And that is how we do this thing. If we this measurement for the 2 state, which is another J state. Here, okay, just to remind you, this now with the selection of certain conditions are that delta has to be plus minus 2 and delta can be 0 plus minus 1 or plus minus 2. So D5/2 has 6 hyperfine layers and we can resolve all of this again using the same technique. Just to give you a comparison of one of the better earlier ones, which seems like the best one before this. This is these are the same spectrum. You can see that we're doing better, and this 3 and 2 is here, and we are also resolving this 1 and 2. Similarly, here we resolve 3 and 2. So we do yellow feet. So we plug the residual because on the feet you don't see any difference. So this
obvious question is what made you better?
so the reasons which made you better is what I was telling earlier. First of all, detecting this. People are detecting other one. So there are reabsorption issues. The signal went down. So we're detecting this. The other thing is that when you lock this laser, people are locking the laser. So now you have jitter in my laser. So and this one jitter, this RF signal have basically they can scan at 1 hertz kind of pitch precision. So those are don't introduce any. So it's a very
Which is so widely explored. That's
Yeah.
why they ignore these things.
yeah. It's okay.
Very
Somebody
widely ignored, of course.
No, people, yeah, so it's okay. I mean, I don't know why, but now, see, it's also, see, this paper mostly before this 2014 paper also. So these steps were not, so people were interested in S2S. S2S is the dogma that we need to do that, but now people are slowly, so now the idea is slightly shifted. So people want to do many steps because some things which theory cannot, so they basically have to run experiments and find out correlations and people will give them the correction. So you have to do D state, you have to do P state.
There are other people doing S to D transitions
Yeah, now there are people who are doing
recently.
in the last 1 or 2 years, just before we published, also we saw a paper which came very trying to do precise measurements. So very which one?
Why they look for the other selection or not what you are looking for?
Which one from? Can you tell me?
72 is something we didn't do.
Why they didn't look for it? Yeah, that I really do not know. So this all we do. No, I don't think that. What we do is that we just use a short pass filter. We are basically using a long pass filter and detecting from here to here. Yeah, I can measure the other one. Yes, I can. There's not technically anything challenge. So I don't know. So these are the branching ratio from this state to this state is 65%. So this is the most. I mean, that tells you already this is what I should be looking at. There's nothing which is not done that. So I don't know why people did.
So the 2 things are you look at that line and you stabilize this laser.
Yeah. And nobody was using this even to scan. So people typically use such similar techniques. So when you have an electro-optic modulator, when you can have sidebands and try to scan this. But these are problems. You cannot do this level of intensity. I'm also separating intensity. I'm separating it into two frequencies. You have two frequencies coming into your laser, and that will show that we can measure small change, how changing the power of the laser out in the next few slides, that how we can measure the full transient frequency shifts. So we'll show you that. Yeah. So okay, good. This one.
If I look at F1 to the 1 and F2 to the 2 on the upper curve,
Okay.
there are you not seeing the earlier paper 2011?
They are not seeing. They are not seeing. They don't have the resolution to see. So yeah, they don't have the resolution. Similarly, here also they don't see these two transitions. They don't. Okay, so this is the consistency check. So this is the data collected over many months and plotted, and we basically reproduce this. So this is now the splitting between these levels, and we reproduce with around 6 or 7 within 6 or 7 players. The splitting. This is for the for going from the ground state, and this is from the going from the x equal to 4 state. So and in agreement, except here there is a disagreement around 60 kilohertz, which is around more than 5 sigma. So I really don't understand why this is happening, and there are no previous levels are not so precise. So they would have everything will fall in their error bars. So so we don't know, but still the other ones are consistent. So
the 60 kilohertz is shown in all measurements.
yeah, so this is the data taken maybe for over like 3-4 months. So each data point is one data averaged over 7-8 times. So each of this is the error bar.
That's real.
So for us it is real. So now it could, some weird systematics could, because we're ultimately fitting and doing a lot of things. It could be something with all AC star shifts, Zeeman shifts, collision shifts, all these things are characterized. None of this can explain this shift. So whatever we know of, whatever we think could explain it, we check, but none of this explain it. So and we don't. So basically, someone has to do a similarly precise experience. See if it is real or not. And earlier experiments don't have this precision. Yeah.
I can't see which one.
You see this, so these are 22.02 splitting. Here it's 22.08. So that's a 60. And this is these are in mega. So this is around 60 kilohertz. Yeah, 60 kilohertz. So our precision is around 10 kilohertz in the. So it's more than.
Error bars are of the order of 40.
This is, you should look. No, these error bars are. See these error bars are not 40, right? I mean, this is the final error bar. But even here, if you look at the scatter, it's around maybe 20. Yeah. So okay. So what could change the signal? You could, if the temperature of the cell dips, then the collisional shift. So we can also we can measure this because which is fixed on a transition with on a cesium transition. Now if we look at the other transition, change the cell temperature of the other one, the frequency of that will shift with respect to this. So this is something which we can do. And so the data I showed you here, this around 135 degrees centigrade, but we can change the cell temperature and we can see that the peaks will shift in position. And I have all the 4 lines which are plotted together, and basically they're falling on top of each other. What is happening is all the 4 lines are shifting, but they are shifting at equal rate. So the hyperson splitting will remain unchanged, but the lines themselves are shifting. So we can measure this collisional shift, this small shift, 32 kilos per millitime. And these are important measurements for clocks. So if you want to know, yeah. Okay. Yeah, so suppose one cell we don't do, one cell we fix at 135, let's say, right? So we know the other cell, if we put at 135, we should see the exactly same frequency of the we should shift from. Now the first one we keep fixed, the second one we tune from 135, 140, 70, 80, whatever. So we can measure the shift. And so it's so
135 plus minus 1.
how many?
What's
How the stability of this thing about the 1 degree centigrade. So our
so that corresponds to what change in vapor pressure?
Here see 1 degree would fall within this. It's not much. I mean, So yeah, so here is something like 10 degrees, you will see this much change. In the vapor pressure, this is a temperature and this is a vapor pressure plot. The same, this temperature are converted into a vapor pressure. So at 135, it's not much, but if you go to temperature, small changes in temperature will change the vapor pressure by a lot. So it's the same data plotted in vapor pressure basically. So from this, if you fit, you can find out what is the collisional shift of these lines. You can also find out what is the line width. You can measure the line width, and the line width increases with pressure, and you can extrapolate what would be the line width of mean zero pressure, and it turns out to be 2 megahertz, which is intercept, and the natural line width is 1.7 megahertz. So we are doing sort of close to the natural line width, but other effects, so like the laser has some finite line width, I said. And then there's some transit time broadening, so that explains, would probably explain why we are seeing something slightly higher. And as Yarke was saying, so if you change the power, what I plotted here, first is the fluorescence intensity and a power squared. So it's a 2-photon process. You expect it to be I square dependent. So I've squared it, so it's a very perfectly linear fit. And these are the using these data points. So we check this as a consistency, and we can also again similarly measure as we change the power. So we keep one cell fixed, everything is fixed, the other laser's power will change, and we measure what is the shift. And again, what we see is that all these hyperfine level shift, but they shift together. So the hyperfine splitting stays the same, but the lines shift. So this is actually a difficult thing to measure. So people can always say that the splitting did not change, but now we have reference also to say how much it will shift with power. And this is also a number which we can calculate. And this shift depends on the polarizabilities of the 7D and the 6S state. So the differential polarizability, and this depends on the matrix elements, lots of matrix elements, which we can take from some database. And we measure, and then we can compare the measurement, which is 49 Hz per centimeter square, and the theory gives 54 Hz per centimeter square. So
Small shift.
very small. So it's very small, but we can measure it. That's the thing. But yes, and it is small. These transitions to what the importance of optical clocks, secondary portable optical clocks, because these are, you can do a simple cell, using a person reading our language, and then if you can calculate how we shift to temperature, then these give a frequency difference. You don't need to only microwave clock, these days much more complicated strontium clocks and all. So there's some these numbers are basically important. So and this is so nice to see this calculation. So it is pretty much. The difference show everything is similar, language is similar. So now we can see from the state and the state, it's currently sure we can find and theory that 1.3. So it's actually the theory is good. That's what this is sort of saying. Okay, that was super fast. Okay, so these first make use of that how we get from so it's not the response, and we IG and cancer and everything. So we can find what this magnetic and A, B, and C. So we start considering slightly lower than it is sort of consistent with it. So we basically have 5 similar waves of and we have bound for the nuclear optical moment, which is C, and similarly for the booster. So we have optical moments in for the 70 states in serium. Okay, so now let's go to Sankar's question. So we find first thing the laser. So we get these lasers. So these are semiconductor lasers which are which are basically 5 millimeter in diameter, and maybe this depending on what wavelength you're looking at, the semiconductor is different. So what we do is we put this laser and collimate the beam and put a diffraction grating. So this I will put P behind the diffraction grating. So now the disruption within this sort of dispersals are available, and we choose the wavelength that we want to create, which is tinted and make it to go into the laser arc, there's an initial lasing action at that particular wavelength. And so the two conditions are given. Right? One is this condition that this angle has to be met, which is to the scientist, the spacing of this grating is equal to lambda, and the other thing is standing with condition of the laser, standard laser in lambda by 2. So now the thing is that if you tune it, you have to do it in a way that these two conditions are simultaneously met, so that the laser can tune without hopping from one mode to another. And we can show that this will happen if the plane of the grating intersects with the plane of the back plane of the laser. And so we can to implement this in our laser, and we can scan the laser for many gigahertz using this just by tuning the laser. And for the feedback also, basically we put the feedback on this piezo. If the laser drifts, we put the feedback on the piezo and bring it back to the laser we want.
So, so you're really saying that the original diode laser is a broadband source.
Much
You are basically putting effectively creating a very fine filter.
right.
It takes out.
Yes, so just in I'll explain that. So this is the if you look at the many tens of nanometers. This small millimeter chip, it's let's say half a millimeter length, at least 250 microns. But these are two surfaces. The back face is highly coated, so that the light comes out. But on this other end, this refractive index change. So therefore, some amount of light will get reflected back, so that will create a lophinous cavity. So that is this diode cavity, which will have some gain. So you'll have this oscillation in the gain. Then on top of that, I have an external cavity which are a long length, therefore smaller free spectral range, C by 12, and then this thing, this blue one, and then this grating which dispersing it, and that has some profile. So you have to multiply all of them, and then this black curve is where it will lace. So now if you try to tune it, you have to be careful because there is a mode competition. It will lace, but if you don't do it properly, then go from this mode to that mode. That's you don't want. But if you do it properly, then you will scan. And once you do it, there is lasing, so it will go from very broadband to few, less than a megahertz basically. So, so this is our first gen. Yes.
You're tuning between one of those two narrow ranges.
I am tuning this profile, this grating I am tuning, right? And I'm also tuning this external cavity because I'm changing the length also. So I'm trying to keep this red and the blue together. Yeah, together, because these other ones are much slowly varying. So I don't need, so this one guide can be, I don't at all need to worry about. And this one I have to worry about if I want to scan from here to here. But for if I'm doing 1/10 of this, then I don't need to worry about it.
The power falls by what?
So if you go from here to here, so it turns out that we also have to tune the laser current if you want to do very well. And then it can be like go from 100 to 10 milliwatt if you do want to do 100 gigahertz. But for a few 5-6 gigahertz, if you want to do it, will fall by, let's say, 5% or something.
So, in nanometer terms, how much is the
Scanning range? 0.01, 02. The best ones maybe 0.02.
Smaller.
Yeah.
Maybe even smaller.
No, I think I have the 100 gigahertz kind of thing. We can, yeah. These are first generation lasers, and this is a spectrum taken with this laser. This is a spectrum of rubidium spectrum with this hyperfine excited state hyperfine resolved. This is our current generation. These are again done in the workshop. This is a CAD drawing. So basically, this is the piezo, and this is the grating, and this is where the laser is gone in, and we are feeding back. We can measure the line width. So how do we do that? The external cavity is between the laser diode is inside this black thing, you see, and this grating. That's the external cavity. Yeah. Some people also call it extended cavity because there are so many cavities in this. But yeah, that is what we are calling the external cavity. In between is free space, air, not vacuum. But we seal it so that there is no air fluctuation. That much we do.
Connected to this part.
This is the piezo. Okay, so yeah, this is the green is the piezo, and if we apply a voltage, it will rotate about this pivot point, and this pivot point is actually aligned quite well with the backplane of the thing. So that's the design thing, and these small wedges you see that we inserted initially in to sort of make sure that the plane is defined well. And in the next generation, we sort of don't glue it separately. We make the design properly so that, and this is also a different material. So now we are making out of titanium. because all these drifts of temperature drifts and all this. So it turns out that this is much better, and so these are super stable now. If you leave it covered and all, it will stay. I mean, let's say 50-60 megahertz for many hours, and you come back, switch it off, come back tomorrow, and switch it on. It will be on resonance. So okay. So now, okay, how do you measure the line widths of these things? So what we do is for this 670 laser. So the reason we wanted to make this 670 laser is right now there is a problem with semiconductors. They cannot make very high power 670 lasers. The one that is commercially available, ECDL, is around 30 milliwatts. But we need more. We had ordered in 2009 an amplifier. It has still not been delivered because there is a shortage. So we said we need something. So there is a laser with this small laser, very cheap, $30-40, which we bought. And we tried to make this ECDL. So the difference is that these things that we buy for cheap, the front face of the chip is not coated. So this reflection is very high. So you have to spend a lot of effort to make it, the external cavity dominate the sort of the tuning. But we did this. So now we made two lasers with two different diodes. And basically we combine them on a beam splitter, put through a fiber so that they are matched, completely spatially matched. And then we slightly offset the frequency of these two. And then we detect them on a photodiode. So because they are slightly different frequency, they will beat against each other, and we measure the beat frequency. If the delta function laser is very narrow line width, you would basically get a. So now you have to do a Fourier transform of this. This is what it looks like. So if it was a very narrow line width, even narrower than this, it will be like a delta function. But this width of this Fourier transform basically tells you what is the line width of your laser. So this is a measurement done with us, and this is we get around 600 megahertz for these lasers, and our powers are 100 milliwatts. So this is right now the best basically laser at 671 in anywhere in the world actually.
The purpose of that special glass that's over the laser is that
this one, right? This one, right? Hermetically seal it, because these are indium gallium arsenide or phosphonite, so that you don't want oxidation or anything. So there's something. Yeah, so yeah, and our costs are like 5 times less than if you buy commercially. And this is not, you cannot buy this commercially, but even if you have to buy it, we are doing much better. Okay, so this is now we use this laser for laser cooling. This is the laser, and this is again a sort of cell. You cannot buy a cesium lithium cell. You have to make it. So this is made in the workshop. So you heat it, make some lithium vapor. There's some challenges. Lithium is very reactive, coats everything, glass and everything. But anyway, we do now a saturated absorption spectroscopy with this laser on this heat pipe. This is the signal. Now you see this is a hyperfine splitting. Now we have subtracted the background well, so that's why it's looking completely flat. And these are the hyperfine peaks. So now we want to, so this is the transition from f equal to 2 to the f equal to 3 of the laser. And we need to lock on this transition. So basically we want to be slightly detuned from this transition. So I'll come back to this one. So what we have, Shankar, is a board which we made in lab. So what we do is we feed this signal into this board, and it's a basically lock-in detector. You take a first derivative and you measure it, and you put a feedback on the piezo so that you always sort of are on resonance. So you can tune it by magnetic field and all, but this is how we stabilize the lasers. And we want to be slightly off resonant. That we can do, for example, with an AOM, just shift the laser beam. And why do we want that? Because suppose the atom, so for laser cooling, suppose there is an atom moving in this towards that direction, and the laser in the opposite direction. If it's moving with a velocity v, and the laser is slightly low energy, then it will see a frequency that is slightly higher. Therefore, it will be able to absorb this radiation, go up, and then de-excite. But when it absorbs, you will get this momentum k, h bar k. So this atom's velocity after momentum after one absorption will be v minus h bar, mv minus h bar k. But this is a cycling transition, remember? So it can happen millions of times in a second. So after a while, it will basically be close to zero. You might ask what happens to the excited state. It's also giving out radiation, so you should get a reverse kick in that. But that is isotropic, so that averages out to be zero. So effectively, if you have one laser beam, you get a momentum kick one direction. So if I have 6 beams, I can give this direction, I can sort of pull them in all 6 directions. And that is what is done in this magneto-optical trap. We have 6 beams slightly detuned from the transition, and you have some magnetic field to trap them. So this is the apparatus. So we take this laser from this table to another table with some optical fibers. You can see probably these blue things which is bringing the light here. And this is the table. So we have this is a chamber. We have 6 beams. These are retroreflected back. This is before we had all the optics, some 6 months ago. And
In the workshop.
this is made in the workshop. We have the central part of the chamber is made by Sourav in Pune. But yeah, many of the other things are made in workshop. Inside also there are lots I'll show you. And this is a signal of a lithium rod. You can actually walk in the lab and see it with your eyes that this is the central glowing is a suspended in vacuum, glowing atoms. It's not a single atom, it's a cloud of 10 to the power 7 or 10 to the power 8 atoms. And they are glowing because of the laser. And you are basically imaging. This is a picture just taken with a cell phone camera. So we have not measured, but should be around 1 millikelvin, slightly less than 1, between millikelvin. Yeah, between half a millikelvin to 1 millikelvin. But we have not yet measured it. So this is what. So if you turn on the laser, this is how the atoms sort of load. So if you look, you can look how much time it takes to load. But and then from this, so what I plot is the fluorescence. But if you know what is your solid angle, you know what is your scattering rate, you can calculate how many atoms are trapped. So that's how we know how many atoms we are trapping, and we can image and find out the size, and we can therefore find the density of the atoms. So after it is loaded, if we sort of block all our beams, then not block all our beams. So I just should mention. So this beam. So we are right now using only this arm. So there is a oven at the very far end. We have something called a Siemens slower, which is pre-slowing the atoms, and then we are doing a magneto-optical trap. So the source is here. So we can block the source using a valve here, so that will stop the loading. And what we do here is we stop this loading, and therefore now it's not loading. So because of collisions with background, this trap will slowly start to decay. Yes. So it's so this is basically like you can think of it as a one-dimensional slower. The same physics we said here. Just in one day. So your atomic beam coming in here, laser coming in this way. So laser is scattering and it's slowing. But the problem is the laser is fixed frequency. The moment it gets slowed a little bit, the Doppler shift changes. Therefore, it will not absorb. So you have to tune either the laser frequency, but you cannot do it so fast, or the energy level of the atom itself. So this is going through a region where there is a gradient in the magnetic field, and there is a profile which is changing the Zeeman shift and ensuring. So we did the simulations. So Mumbai actually did the simulations, and with another project student earlier, where we can match this. So this is standard, by the way. I'm not tech. We are doing it alone. So we can match this, and it's called a Zeeman slower because it uses Zeeman effect, and therefore you pre-slow it, and so you will go from some 800 meter per second to around 100 meter per second, and that is slow enough that you can capture a lot of them in this 6 beams, which have a some typical time, maybe 100 meter per second they can capture, not more than that, because they have to cool. They have to get the atoms enough time to go through the laser beam and get cooled before they escape. Yeah.
So you're using like Helmholtz curve or what along the?
Yeah, so this is like a solenoid. So we make this. So maybe I'll show you a picture. It's a solenoid which with wires that we write with a number of turns determine what is the magnetic field profile. Yeah, we make these in the workshop. Maybe I have backup slides I'll show you. Yeah, this is made a lot. Everything is basically made in a lot of instrumentation have gone into this. Yeah, and this, by the way, is the cell where we do this experiment. These are these wires you see, these are for degaussing. So you can in situ degauss these things and make sure that your fields are zeroed. Okay, where were I? Yeah, so this load from this you can do some integral is very preliminary. But if I plot it in the log scale, this is what I see. So if it was only collisions with the background gas, it would be a single exponential decay because it's a one-body process. But what you see is that towards the end, it is a one-body process, but initially it's a faster decay. You can also fit this fellow and you will get 2 times constant. So what is happening is initially when you have a cloud, this is very dense. So there is a collision between the cold atoms themselves. And therefore, so you can, and after a while, some atoms have gone out, the density has reduced. So now it's the 2-body collisions goes down. So it's only the 1-body collisions with whatever remaining atoms in the vacuum. So we have vacuum about 10 to the power minus 11 milliwatt. It's a very good vacuum, and that is why you can trap them for like more than 3 minutes in the trap. Okay, so this will give us basically our. So we are right now measuring this. So we'll try to measure the collision rates. So if we know this decay, we can model it, and from this model we can find this 2-body cross beta the collision rate constant, and from that we can find out what is the cross section for this atom-atom collisions at this kind of temperatures. Okay, so we are right now, so this is a top view of the apparatus. We are using this arm. This is the laser beam, the way Shankar was asking. This is the slower vapor get created here, and this is slower along this arm. So this is for lithium. We have two other arms here. Here is the arm where we have cesium and potassium, where we will do a pre-slowing in a different method and send them and trap them. So that's our goal, to trap at least two species together. And this also has ion trap in the center and a spectrometer on this axis. So the ion traps, if you ionize these atoms or you create some molecules, this is one of our goals, to create molecules, let's say, of lithium and cesium. And how would you detect them? Typically you ionize them. So you create an ion of lithium cesium plus. We have this done by, again, the TIFR workshop. We can trap them. We should be, we have not done this yet. And then we can also do mass spectrometry. So the mass spectrometer, again, so these are the Heinzel lens for the mass spectrometers. These are built in a workshop, and this is our ion trap inside the center. At the center of this is the mod. So this is before we assemble everything, is top view of the picture. So everything can ions can be trapped, molecules can be created, and a mass spectrometry can be done. Okay, so I think so this is I'm run out of time. So, but yeah, our initial plans are to make molecules to create another species of cold atoms, which should happen in a few months, and then we want to associate them. There are techniques called photo association and also magneto association. You can tune lasers and create from free atoms to bound states. And this depends on the density of the atoms and all. So that's why we are interested in high density atoms, because then you want two body collisions to dominate to make this process more effective. And then so this will create initially in some state, then you want to control which state we are creating or pump them to the ground state. And one of the things we will initially look at is this collisions and very ultra cold chemistry. So then when they collide, a lot of things are unknown right now. If you basically, people see that if you put two molecules, they even at this cold temperature, they collide very softly, but they don't stay, and they just disintegrate. And why they disintegrate and how, and it cannot be captured by just two body collisions. So that people are theoretical, it cannot be captured. They say that this should not happen, but it happens. So we'd probably like to see if we can answer some of these questions. And eventually we'd like to actually put these molecules in something known as an optical lattice. So the reason for choosing two different species is because they have different electronegativities. So now you have two atoms with different electronegativities, therefore they have a dipole moment, permanent electric dipole moment. So you can align them with electric fields. And if you put them in a lattice, now imagine you align them, they have a dipole-dipole interaction. And we'd like to, so this is you have seen, I'm sure many of you may have seen, this is a picture with people showing atoms in lattices, but the two atoms in different sites don't interact. So they are basically not interacting. This is these two separated by even half a nanometer, half micrometer will interact. Interact meaning in a sense that we can measure. We can measure with a laser frequency that this is the energy shift I'm seeing because of the presence of the other ion which is interacting with. Yes.
So you want two molecules into neighboring values, or you want the entire array?
We would like to have as many.
That takes that number n of interaction.
We can also do it too. So the challenge is not filling. The problem is having a unit filled array is a problem. Like if you want 10, it's very much more having a
molecule per value is
difficult. To ensure. So people are right now have device ways for atoms how they can manipulate and put atoms in one valley. But in molecules, it's more challenging because you see you are starting from atoms. So when you make molecules, your density has gone down a lot because there is about a factor of at least 10 decrease in the density. So you have to do something more because initially see our molecules are formed from the atom centers. But people have done it. There's some unit filling in some 30 lattice sites. So people are, Okay, so I think I'll stop here. Thank you, Shovik. I want to show you that thing. Where is it? So this is what the made solenoid. This is what we started with. So this is what fabricated in the. So there are many sections, and then there are wires which has been wrapped, and these are this gray color thing is something which is a epoxy, which basically resists high temperature, but it's a very highly conductive epoxy. So that's, but yeah, this is the what I was asking, Shankar was asking. This is a simulated field, and this red dots are the measured field. So we sort of try to ensure that we are doing this thing. Okay, thank you. And thank you.
Thank you. Thank you. There are quite a few questions for us. A lot of discussion took place, but if there are more questions to the speaker, yeah.
So, your double exponential was kind of eye-catching.
Yes, go ahead.
The two exponentials are very clearly separated in time.
Here in this one, right? Here, but this might be mean biasing you, but yeah, I thought that it is sort of, but I said it's preliminary, so maybe it will not be so once we repeat an average, maybe. But it is true that there are two exponential decays. So if you, okay, so if I had asked you, I not you, but anybody or my student at least, that okay, let's look up to here, let's say up to 10 seconds or 50 seconds even, and tell me when do you expect, fit it, and we have data where we just stop it at 50 seconds. Then you will say that this is going to 0 by some 120 or 120. And this is, by the way, so this you see from here to here, you have one small few dots. That's because we intentionally switch off this laser, because to see that whether we still have an atom. So if you continue, this basically holds for a very long time, now much more than sort of this what is shown here. So, but then yeah, it just keeps going. It becomes fainter and fainter. You can see it with your eye also, and it will keep going. So it's not a single part. If I fit different parts, like you will always consistently get to different decays. Yeah.
But this Mumbai,
see, this decay is nothing special. Decay is just that, however, these are measurements. Yes, people know that this will happen. Yes. Yeah, people try to. So this is, if people are interested in studying two-body interaction, this is how people will do it in this community. So they, yes. Yes, you will expect that two-body decay. So see, this is the basically the simplistic model is for this decay is this, that you have a loss rate from the vacuum, which is one body loss rate, and you have a two body. You can also have a three body. You can add a three body term and try to measure it. But we can do that. But I guess our densities are not that high that it will show. So then you will have a third time constant coming. But I don't think we are there yet.
Yeah, something more? Yeah, okay, just hold on. Yeah, go ahead.
So suppose you want to measure for the other system.
Yeah.
So do you need the same isotopes in two cells, or the one cell is fine and the other?
Wait, two isotopes. You are talking about the hyperfine pressure. Yeah, I don't need. So I could have stabilized my laser with anything else. I could have stabilized with rubidium as well. Yeah, as long as the laser frequency, rubidium has some iodine, which iodine has a molecule. You could have, you could take a transition which is near that, and stabilize your laser. That is only for stabilization. So I could do it that way also. So it's not required that the second cell should be of cesium. It helps us because it's cesium and we are locking on a 2-photon transition, which basically nobody does because it's a weak signal. Why would people want to invest? But we do this because now this signal is very narrow. So when we lock the laser, it is locked to like less than 50 kilohertz sort of stability over many times. So if you just do with iodine, you will maybe doing at 1 megahertz or something. So because our signal itself is so narrow at 2-photon, we can lock also very well.
No, this question is that you want to do cesium, you're done with cesium already.
I can use this cesium and yes. Yeah, we can do it. So I think his question is that do I need 2 cesium cells? No, we can use. So I need only 1 cell of cesium. Yeah, 1 cell of cesium 35 is fine. But that has to have enough density. That is the point.
Okay, I would like to go.
No question is to be.
How you manage the gravity? Second,
manage the gravity. Okay, and
second, if you use the broadband laser, can you get rid of Zeeman fluoride?
Yeah. So second question first, let me answer. If you would have broadband laser, you could, but the problem is that broadband laser at each frequency there is not enough power, right? So right now we have narrowed the frequency to 1 megahertz. So all the power is in that 1 megahertz, and the line width is around 5 megahertz. So in all the power in the laser is going into cooling. You have a broadband frequency, then you have all the frequencies, but you do not probably have enough power in each of these frequencies. But there is one other way to do it, which is that what you could do is you could take this one laser and you could use an electro-optic modulator and create sidebands. You do this like we are using an AOM to shift the frequency. You could get 1 megahertz, 5 megahertz, 10 megahertz, and you can like a home. So now you have enough power. It's not that broadband also. Maybe it's 100 megahertz broadband. You have enough power. So that you can send and that you will see as event cooling. The other thing is that you can do is that you can try to scan your laser frequency very fast. This is called chirp cooling, and therefore now you are covering before the atom. So the atom may be taking from here to here. It's taking 1 millisecond. If you can do at 1 microsecond, you are scanning your laser at over the entire 1 gigahertz. Then maybe you will get a cooling. So that's the thing. The second way. First question: how do you suspend against gravity? So although this photon seems to be applying very little force, actually, if you do the calculation, how many it is much higher than g. If you have to guess, can you guess how many higher? It's enormous. It's 10 to the power 5 g. So 10 to the power 5 times the gravity. So gravity has not, it doesn't have any chance here. So in this kind of sort of laser cooling, magneto-optical trap. But if you remove the laser cooling and do some other trap like a magnetic trap, then you have to take care of gravity. There it can become comparable. If you don't suspend enough, then it will sag. But here it's many times higher. Yeah.
I think let me go first.
No, I think coming back quite a bit. So, is your thing isotopically pure?
Cesium has only one stable isotope. So that is where my cesium is isotopically pure. Lithium, for example, has 2 isotopes. Rubidium has 2 stable ones. But the isotopes have slightly different energy levels. So when I measured this, there was a plot where I showed this rubidium in our laser. I didn't explain it. This is for 87. This is for rubidium 85. So they are spectroscopically you can separate. They both are there in the cell, but their spectroscopic signature is different. They are slightly shifted out. And this is so basically you can do isotope shift measurement. That's again what people are doing these days to compare with nuclear physics. People have become very interested in these things. So I think there's a lot of.
Yeah, I think.
Just wondering, so you make this ECDL lasers, no, from this regular lasers that you buy at the market. So what do you do?
What do I do, meaning?
I mean, so basically you put some reflector or something.
No, I buy this one.
Okay.
I buy the grating. I buy the lens. I buy the piezo. But so a grating is maybe $60-70. Grating is another $60-70.
Well, you say to convert like okay, you're making the whole.
You assimilate the whole.
Yeah, but the but the problem is okay. So the problem is that you might think okay, this is not. But this laser also I have built. This laser is also I have something I have built. So it matters that how you build it. Yeah.
But this is being built in laser cooling for a long time. Like
Yeah.
people always make the ECDL.
Yeah.
Because the commercial ones, they don't.
They are very good, but for the lithium we had to make because for 2019 we are waiting. I mean there is no amplifier.
Those are what they are compact.
No, it's the same size. They will have the same size. It's much cheaper. It's much cheaper.
times
But
cheaper.
we didn't make it because we just had to make it because 2019 we had the lithium, the 670 there is a problem. So there is only one company who can manufacture these semiconductor diodes, and they have run into some problems for the diode also and also especially for the amplifier. So they have jacked up the price initially, but people still placed orders. So mine is from 2019 and it's still not delivered because they are not able to reproducibly produce this. And one of the challenges in this amplifier is that in the amplifier you want both the surfaces. So in the amplifier, laser enters and then exits. So both the surfaces have to anti-reflection coated, and that is very challenging apparently. Also, there is some problem with the gain. So other amplifiers can give you like 780 or 850 nanometer. You get 4 watts of power with amplifiers. Lithium 670 is still limited to about half a watt, and that also unreliable. So we had to make this laser basically. And so all this laser cooling is with that one single laser. I mean, so. Of the laser because we have so much enough power. Diode this diode is the diode, this proprietary thing that is that only they can sell. So what I am buying is from a generic market. This is not meant for this kind of experiments, and the difference my guess is that the proprietary thing has a very nice air coating on the front facet. So you will not have to have competing modes. The generic ones don't have this. The generic have some reflection going back. So you have to design things and make sure that you have enough feedback and enough stability that you can still use it in an experiment.
Yes.
This is in gas is the 6780. So these are some phosphide in gas phosphide, gallium arsenide.
Huh? So
No questions from you.
I'll just try. I'll just look at. I didn't see any questions, but just hold on. No questions, I guess. Okay. So if there are no more, no, that's okay. If no more questions here, I think let us thank the speaker again and also give him this little.
Thank you. Yeah, thanks.
Okay, please join for a cup of tea.
So the next time can you speak a little slower when you're delivering?
You will close. Yeah.
I thought I don't want to come
No,
between.
actually, the problem.
Yeah, Friday.
For people on the Zoom.